you're interested in evaluating the performance of your hybrid MPI and OpenMP application, you may be interested in our hands-on practical hybrid parallel application performance engineering tutorial by the VIHPS group. Now, in this tutorial, we will introduce the VIHPS tools and basic concepts of parallel performance engineering. We will also provide an OVA file which will be loaded in the VirtualBox software, and we will also have hands-on sessions on Stampede at TAC. The first tool we'll describe is the ScoreP instrumentation and measurement toolkit, which will add hooks to your code to perform the measurements. These measurements will profile and trace the application. While profiles can show the summary statistics of the performance metrics, tracing can go deeper and show us exactly what each process was doing at any given point in time along a timeline display. We will look at the call path profiles using the Cube profile browser. The ScoreP measurements will be customized, and we will create filter files to create compact instrumentation so that the runtime dilation of your application is minimal. The profile files that are generated will be visualized using Tau's Paraprof profile browser as well. We will generate trace files using the OTF2 format and use the Scalaska toolkit for automating the analysis of these traces to extract information or knowledge about the inefficiencies and when and where they occur. We will collect this data in the form of performance properties or bottlenecks rather, and view them in Paraprof and the Cube profile browser. The traces will also be visualized using the Vampire commercial trace visualizer, where we can see the timeline view and see what each rank and thread was doing along a timeline. We will also look at the specialized ScoreP measurements using hardware performance counters, and then we'll look at cross-experiment analysis using Tau's Perf Explorer tool. We will conclude the tutorial by discussing typical parallel performance bottlenecks and how they occur. So the first tool we'll look at is the Cube tool. Now Cube has these three dimensions. There is the metric dimension, then there is the program dimension, which consists of the call tree and the flat view, and then the system dimension, which shows you where a performance property occurs on the system. So here, if we want to see the profile of this NAS parallel benchmark, we can see the total execution time by expanding the metric tree for time, and it's laid out in a hierarchy. So these metrics show you in a very easy to understand manner what is the total time in computation, in MPI and OpenMP. If we click on computation and expand the call tree, we will be able to see what each function was doing. So for instance, in this color-coded chart, we can see the ysolve, xsolve, and zsolve functions. We can see the OpenMP parallel region, the OpenMP do loops, and the barriers that take place, and see them along the system tree so we can see the impact of that particular function on MPI rank 0, 1, 2, and so on. And we can see the time spent in each thread. So by looking at the performance metric along a given call tree and the system tree, we can pinpoint the total time for a given region of code on a given process or thread of execution. Now, Scalaska can be used to find performance properties that give us key insights into what's going wrong in the application. So here, I can see the communication, point-to-point communication, and the late sender performance property. If I want to see the info, it will show me the time in MPI point-to-point receive operation waiting for a message. These messages are caused, the performance property is the late sender bottleneck because of messages in wrong order from different sources. So there are a variety of different bottlenecks that you will be able to see. Here is the idle threads, and you can see MPI wait all and the impact on different threads in seconds. I can also expand and see delay costs. Here I can see the MPI point-to-point late sender bottleneck because of short-term or long-term delay. And I can just always click on the info or documentation. Here it says delays that are indirectly caused by MPI late sender wait states through wait state propagation. And you can get more information about this. You can also see critical path information over here and the imbalance along the different program entities and threads over here. So Cube provides this three-dimensional view which shows us the performance properties, the call tree, the flat view, in the system tree, or even the box plot view. We can get a lot of interesting information and the performance impact of the code through the critical path, non-critical path activities, and measure the precise imbalance in your application. The second tool that I'm going to show here is the Taos Paraprof profile browser. Here we can see all the MPI ranks, and these are the various functions, loops, and routines that are instrumented in the application. Now let me go and stack the bars separately so I can see the contribution of, say, MPI barrier to the profile. I can view this data in a 3D visualizer. As part of the Paraprof, I can see along one axis the MPI ranks, along the other axis the routines or loops, and along this z-axis I can see the exclusive time spent in the function in a triangle mesh or a bar plot. So I can see the shape of the full profile. If I want to find out what a given function is, I can look at these two crosshairs. There's a function crosshair and a thread. If I move the function crosshair and I see the thread, I can see the time spent in various functions. So here in this loop on thread 199, I see that it took 129.5 seconds. I can zoom in, I can zoom out and find out outliers. I can click on the scatter plot and see that one MPI rank was different from all the rest in this particular code, where I can see the maxima and minima along these three dimensions and along the color dimension. The maxima and minima time spent in each of these functions, and each rank is a unique ball over here. So once you have generated the profile data, you can also store it in the Taos database and access it using the Perf Explorer tool. In this case, I have generated performance data on 2, 4, 8, and 16 core counts. And then I can see the total execution time in this code and measure precisely what happened. So here is an example of an aligned bar chart where I can see the time spent in the MPI wait all and how it decreases, the time spent in do loops, and what happens to this time across different core counts. I can look at the runtime breakdown and see along the number of processors what each region of the application, what each event contributed to the overall profile. So along 100% time axis, I can see which functions take a higher contribution and which start increasing in size. You can also customize it and look at custom charts and put any metric along the X and Y axis and generate custom charts using Perf Explorer. To look at the traces, we will show the Ampere trace visualizer. Now here I can see the total execution of all the MPI ranks and threads for this application. And I can click and drag and see exactly what was going on at a given point in time. This is the summary view, uh, and I can see the time spent in this region from 10.8 to 13.8 seconds. And I can expand this and see what each rank and each thread was doing along this axis. So Vampire is a very powerful trace visualizer, and it can highlight the load imbalance in your application very easily. If you're wondering how we generated this data, well, let's look at the NAS parallel benchmark, and let me just make clean and build this benchmark. Now I'm building it without any -G, or just with the O3 optimized option. And instead of running this code like this, I will use MPI run minus NP4 tau exec -t scorpy. Now this will preload the tau library in the context of the executing application, and then it will call the scorpy measurement library and then generate the profiles as well as traces. The profiles can be visualized using Cube or Paraprof, and the traces will be visualized in the Vampire trace visualizer. So here is the Scorpy data, and I can say paraprof profile.cubex and visualize the profile. Here is the 3D visualizer in a bar plot, and I can see the time spent in MPI receive on rank 0 was 8.6 seconds in this application. Now, this is an application that's running in the HPC Linux virtual machine. And here I will look at the traces, and Vampire can be used to load the OTF traces. And it can show us along a timeline what each rank was doing and see the precise time spent in MPI receive, MPI wait, and so on.